Welcome to Keith's Pre-Calculus. This is section 4.5 in the book, Graphs and Transformations of the Sine and Cosine Function. Just do a little bit of a review like we did in class. We looked at the graphs. We see here we have the function, the sine function, y equals sine of x. And we can see that in one period from 0 here to 2 pi, you get one cycle, one phase of the sine wave. I've expanded it a little bit down here so you can see that it is periodic. It continues forever in both the positive and the negative direction, and you get this sine wave going on forever and ever, with one phase being 2 pi length, or one cycle, or one period is the best way to say it, going from 0 to 2 pi. And this is the basic sine function. Now I'd like to look at the basic cosine function. You can see what it looks like. Now we're going to look at these in much more detail in a little bit. I just wanted to show you one period of it, and then down here you can see that it goes forever and ever, both in the positive and negative direction, because its domain is infinite. Here I put the two graphs one on top of the other so you can see how similar they are. The sine function and cosine function, remember, are complementary functions. And as you can see, they appear to be shifted 90 degrees horizontally from each other, or pi over 2 radian horizontally from each other. It appears that cosine is shifted pi over 2 radian, or 90 degrees left of the sine function, because they are complementary, so that would make sense. They have the same amplitude, they have the same period, but they have different x and y intercepts. Oh, and they have the same maximum and minimum, and we're going to be talking about that in a minute. And they also have different symmetry. So let's look a little bit closer at the sine function, the graph of the sine function. We can see that its period goes from 0 over here to 2 pi. One period in the basic sine function goes from 0 to 2 pi, just like one circle goes from 0 to 2 pi on the unit circle. We see that its maximum point is going to be at 1, and its minimum point is going to be at -1. That's in the y values. So that's its range goes from -1 to 1. Its domain is infinite, or all real numbers, as we saw on the previous graphs. And its x-intercepts are going to be at 0, 0, pi 0, 2 pi 0, and so forth, all the way. We take in the what numbers of cycles it is times pi, and then add 0. And so we'll have infinite x-intercepts. Our only y-intercept is at 0, 0. The sine function is an odd function. The sine of negative x is the same as the negative of, or the opposite of, sine x, and it is symmetric about the origin. Now I want to go back and talk about period. Period is the length of time, or not time, but the length it takes to go from one phase to complete one phase, I should say, to complete one cycle, or to complete one wave, I guess is the best way to say it, before it starts repeating itself. The amplitude is how high it goes from its midpoint to the maximum, or how low it goes from the midpoint to the minimum. So the amplitude of the basic sine function is 1, because the mid line is at 0, or the x-axis, and the highest point it reaches is the 1 up here, and the lowest point it reaches is -1, and that's a distance of 1 from the midpoint. So its amplitude, or how high or low it goes, is 1. Now let's look at the cosine function, or the graph of the cosine function. We can see that its period is also 2 pi. It goes from 0 over to 2 pi. Its domain is infinite, or all real numbers. The range goes from -1 to 1. the y-intercept is not at 0, 0, but it's up here at 0, 1, and the x-intercepts are at pi over 2 radian and 3 pi over 2 radian. But it's one wave, goes from 0 to 2 pi, so its period is 2 pi. Maximum values, I didn't write maximum and minimum values, but they are positive 1 and negative 1, so its amplitude is 1. This is an even function. It's symmetric about the y-axis, but it's even because the cosine of negative x is equivalent to the cosine of x. Let's go back to the graph of y equals sine x. You're going to need to memorize how to graph this by hand. And the way you're going to do it is you're going to look for 5 key points. You're going to look for the maximum and the minimum and the 3 places that it crosses the x-axis or the x-intercepts. So you're going to be going from 0 to 2 pi, and it's going to cross again right in the middle at pi. So those are going to be 3 points that you would graph, or you would plot on your xy coordinate plane, and then you would plot its maximum point in the first cycle or the first phase, which would be at the point 1 or pi over 2, 1, and then its minimum point would be at the point 3 pi over 2, negative 1. And then you could just connect the dots. You are going to divide this into 5 equal parts. You've got 0 or 4 equal parts, but 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those are 5 numbers, but the 4 parts are going to be the 4 quarters, going from 0, or like you can think of the 4 quadrants, from 0 to pi over 2, from pi over 2 to pi, from pi to 3 pi over 2, and from 3 pi over 2 to 2 pi. It is symmetrical about the origin, so if you were to continue going to the left, it would look like this up here. So you can see that it's symmetric about the origin here. For every x value, there's also a negative x. For every xy, there's a negative x, negative y value. And then for cosine, if we go back down here, we would still have the 5 parts from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi, the 5 points on the x-axis, but and the 4 quadrants, the 4 parts. But here it crosses at pi over 2 and at 3 pi over 2. Those are our x-intercepts, and then it's got 2 maximums at 0 and at 2 pi and 1 minimum. So still 5 parts, but in the cosine, you have 2 intercepts and 2 maximums and a minimum. With the sine, you have 3 intercepts, 1 maximum and 1 minimum. And you would just plot those points and graph them just like you see here. Now, what we did not get to in class today because of the quiz is the transformations that happen on the sine and cosine function. So you're not always just going to graph y equals sine x or y equals cosine x. That would be boring. You want to add a little spice to your life and start doing some transformations on your graphs. So we have our basic transformations here. Y equals d plus a sine of bx minus c, or y equals d plus a cosine bx minus c. And we're going to talk about what the a, b, c, and d mean with these trigonometric functions. And I will show you what they look like on Desmos. Okay, a is a vertical stretch or a shrink, so it's a number that's a coefficient that's multiplied by sine, or the sine of x is multiplied by, or cosine of x is multiplied by. It stretches your graph just like the a value would in other functions. It either stretches it or shrinks it. If the absolute value of a is greater than 1, so it would be like 2 or negative 2, which would be 2, or 4, or 1.5, or whatever. If the number is greater than 1, then it's going to stretch the graph. If it is, the absolute value is less than 1, that means it's going to be a fraction between 0 and 1, or a negative fraction between negative 1 and 0. Then it's going to shrink the graph. That is called the amplitude. It determines what the maximum points and the minimum points, how high it grows or how low it grows. So, and remember the amplitude is half of the max to min value. So if you've got from negative 1 to 1, that's 2 units. Half of that unit is 1. So the amplitude would be 1. And then if A is 1, then you wouldn't see it. Also, if A is less than 0, not the absolute value, but if it's actually less than 0, so you have like -2 times sine of x, then the function is reflected across the x-axis, just like it is in other functions. Now we're going to go to Desmos and practice seeing what A does to a graph. So here I have this red graph again of y equals the sine of x. If I put an A in front of it, so I'll put this 2, and I graph 2 times sine of x, then it's basically I've done the transformation A times sine of x, and that would be, do you see what happens with this green one? It changes the amplitude. It takes the graph and it, like a rubber band, it stretches it up or stretches it down. So my amplitude changes. So instead of going from 0 to 1 or 0 to -1, it now goes from 0 to 2 or from 0 to -2. My amplitude has changed. It has become the absolute value of the A that's multiplied by sine. So my amplitude is now 2. And 2 is half of 4, and going from -2 to +2 is 4 units. 0 is in the middle, so the amplitude's half of that 4, which is 2. Or it goes from the midpoint up to 2, and the midpoint down to 2. Do y'all see that? Now what if I took it and I made the absolute value less than 0? If I said 1/2, whoops, 1/2 sine, oops. See, I'm no good with this. Sine of x. See what happens here? See the purple one? It shrinks the graph. It's a vertical shrink. So my amplitude is now half of what it was. And instead of going from 0 to 1, it goes now from 0 to 1/2. See right here, this is a 2 up here, so the 1's right there, that's a 1/2. And it goes down to -1/2. So my amplitude is 1/2. The range goes from -1/2 to +1/2. So the range is only 1 unit, but half of that is 1/2, so my amplitude is now 1/2. So do you see how A affects the sine function? It does the same thing for the cosine function. Here you see your basic cosine function. Its amplitude goes from 0 to 1. But if I were to multiply the cosine function by A and let my A be 2, then let's put x here. Do you see how it changes the amplitude? And now it goes from 0 to 2 or 0 to -2. So it stretches the graph. Same thing if I were to divide it by 2 or multiply it by 1/2, cosine of x. See how it shrinks it? It does the same thing for the cosine function as it did for the sine function. Now we're going to talk about what B does to the graph. B is a horizontal stretch or a shrink. So instead of being vertical, it's horizontal. So it's going to change the period of my graph. Normally, a sine function has a period of 2 pi, and a cosine function has a period of 2 pi. But when I introduce a b in front of theta or in front of x, so some coefficient of x, then it changes the period. And my period now is 2 pi divided by b. Okay, so that means if b is between 0 and 1, the period becomes bigger than 2 pi because I'm dividing by a fraction. And so that means I'd be like multiplying by the denominator. So it would be a horizontal stretch. And I'll show you what that means when we go back to Desmos. But the way I think of it is it's a longer period. The period's bigger than 2 pi. So there's fewer phases that fit into 2 pi. I stretch it out, and it takes longer than 2 pi to make one period. There's fewer phases that fit into 2 pi. But if b is greater than 1, if my coefficient of x is bigger than 1, then the period is less than 2 pi, and I have a horizontal shrink. In other words, it's a shorter period, so more phases fit into 2 pi. And we'll go to Desmos, and you'll see what we're talking about. So here I am at Desmos, and I've got my sine of x. If I let the coefficient of x be bigger than 1, I'm going to make it 2. 2x here. I want you to see what happens to the graph. all of a sudden, my phase, I can fit, do you see how the red one, the period goes from 0 to 2 pi? 3 pi over 2, 4 pi over 2 is 2 pi. It's hard to see with that black line there, but it does. But here my black one goes from 0 to pi, and then from pi to 2 pi again. There's 2 of them, twice as many that fit into the original period. So if we look over back here at these instructions, if b is greater than 1 and 2 is greater than 1, then the period is less than 2 pi. My period was just 1 pi because it's half of that, because 2 pi divided by 2 is 1, so my period is 1 pi. Then I have a horizontal shrink. It's a shorter period, so more phases fit in the original 2 pi. I go back to Desmos, you can see what I'm talking about down here. Okay? Now, if my b is less than or between 0 and 1, let's say it's 1/2. And come out here, x. What happens? Oh, it's giving me a red one again. I wish it was a different color. Let's see if I can make it a different color here. Control C, Control V. Nope. Sine of 1, whoops, 1 divided by 2, x. Yes. Let me do that here. There we go. So now I've got a different color. So now you can see, compare, and you know what, I'm going to X out this black one here too, that'll help. Compared to the original graph of y equals sine x, if I let my b be 1/2, which is between 0 and 1, do you see how I've stretched my period? And now it takes, well, let's see if I can scoot this over a little bit or make it smaller so you can see it better. It takes twice as long there to 4 pi. That's harder to, there we go. So instead of going from 0 to 2 pi, one period now goes from 0 to 4 pi. It puts fewer periods, or fewer, I don't know how to say it, fewer cycles in the original period. This is how I phrase it. It's a longer period. It takes longer to get through the whole thing, so there's fewer the phases that fit into 2 pi. Down here, do you see where I have it right here? Going back to Desmos, we can see that it takes a whole lot longer for one period to happen when I multiply, or when my coefficient of x is smaller than 1, but bigger than 0. In other words, it would be the same as saying, if I come over here to, back over here, 2 pi divided by b. Well, 2 pi divided by 1/2 is really the same thing as saying 2 pi times 2, which gives me 4 pi. So as you can see on the graph, that my period is 4 pi. And it works the same way with cosine. Only this time, instead of doing 2, I'm going to say 3. So I'll just say cosine of 3x. Oh goodness, do you see that right there? How it makes 3 of them fit into 2 pi. So instead of going from 0 to 2 pi, it goes from 0 to 2 pi divided by 3, or 2/3 pi. And then you've got another 1/3 pi, so, and then another 1/3 pi. So 3 of them fit in there. Okay. Or I could say the cosine of 1 divided by 3 x. Oh, it's going to be red. Well, it doesn't matter that it's red. I'm going to X this one out here. If I if I multiply by 1/3, then all of a sudden it stretches my graph, and it takes 3 times as long to get one phase in. So it would go to 6 pi than it would to get one period in than it would to get one, or the original period. So because 2 pi divided by 1/3 is the same thing as saying 2 pi times 3, so my new period is 6 pi. Do you see that? I'm going to skip C for a minute and go to D. D is pretty simple. D is just a vertical shift or a translation up or down from the x-axis or the midline. So if you add something, like add 1 or 2 to your original, then you're going to shift your midline up. And then you'll change your maximum and minimum, so it'll change your range. It does not change your domain, but it shifts the midline up. It doesn't shift the amplitude. It doesn't shift the graph left or right. It just goes up or down. And it doesn't stretch it either. So let's go ahead and go to Desmos and practice that. Show you what that looks like. So if you let me, whoops, can't get to it. There we go. I'm going to X this out. So if I would say the next one, let's just say 2 plus sine of x. I don't like this black color, but whatever. It just, 9x. What did I put that for? There we go. Oh, it's green now. Good. So do you see how it takes this, instead of it being along the midline being along the x-axis, it shifts it up 2 points, 2 units, and now the midline is along the number 2. My amplitude still goes from, is still 1, it still goes from 2 to 3, or from 2 down to 1, but I've shifted everything up 1 unit, or 2 units, I'm sorry. If I were to add a -2 to it, or let's just do -3, just be different, plus sine x. You see how it shifted everything down 3 units. And it would work the same way for cosine. I'm not going to go over it. It does exactly the same thing. So D is just a vertical shift up or down. It's no stretch. It's no shrink. Just vertically up or down. If it's positive, the midline goes up. If it's negative, the midline of the whole thing goes down. It does not change amplitude or period. The last translation we're going to look at is C. And just like you had the H and the K before, this would be my H, and it's minus C, not plus C. And it changes, it's a horizontal shift or a horizontal translation. It moves the graph, the whole function, to the right or to the left. It affects what we call the phase shift. One cycle or one period without a shift goes from 0 to 2. So the left endpoint is 0 in that phase, and the right endpoint is 2 pi. Didn't mean to say 0 to 2. I meant to say 0 to 2 pi. One period goes from 0 to 2 pi if there's no shift. But if there's a shift, it changes where my left endpoint starts and where my right endpoint ends in one phase or one cycle. And then it will continue to infinity, going to the right and to the left. So it's a horizontal shift or a horizontal translation. And the way we figure that out is we say originally my left endpoint is 0, right? But what I'm going to do is I'm going to take this entire value here, bx minus c, either with sine or cosine, and I'm going to set that equal to 0 and solve for x. So I add c to both sides, and then I divide by b, so my x is equal to c divided by b. That's the beginning of the phase. That's the left endpoint of my phase right here. And that's how far I'm going to shift it right or left, depending on whether or not c is positive or negative. Now, the right endpoint is going to be 2 pi if there's no shift. So I'm going to set bx minus c equals to 2 pi to see what my new right endpoint would be. So I'm going to add c to both sides in the divide by b, and I get x equals 2 pi plus c divided by b. So my right endpoint, or the end of the phase, is at 2 pi plus c over b. You need to learn what I've boxed here. This c over b is the left endpoint of my new phase, and 2 pi plus c over b is my right endpoint of my new phase. The period hasn't changed unless it's affected by b. That will change the period, but c affects where it starts and ends. And this will give you your 2 endpoints for the first one, and then you can continue going for the other one. If we go here to Desmos, we can see that I have shifted this. I've put a 2 in place of c, and you can see how the graph has shifted 2 units to the right. So my new period starts 2 units past 0, and it goes to 2 units past 2 pi right here. Not 2 units is different than 2 pi units. Okay, so you need to be careful with that. I am running out of free space, so I'm going to have to stop this video and see if I can make another one with some examples on what to do for homework.